I forgot what chapter it is. This is programming the PLC, whichever chapter that is. We went over the rules, right? Everybody okay on rules? Yes, no. What I want to make sure we understand is this guy right here, Rule 10. So it says input relay contact instruction address can be used multiple times within the PLC program. Output instruction addresses should only be used once. We do have two that is allowed. This is called output last and output unlast. But what I have here is I brought up RS Logic 500 and I did a program. And what I've got is that I got three different inputs, but they're all trying to control the wall. Same output. But so I'm going to go ahead and download this into the PLC. And I'm going to call it duplicate output. That way I can get it next time I see it. And it says, okay, are you sure you want to download the program? We got the PLC in remote mode, right? So it switches between these. Switches auto run mode, switches to the program mode for us. Then it's going to switch back to the run mode for us, and then it's going to go on. So right now all the outputs are there. And what I'm going to do is I'm going to close output 0. Why didn't output 0 go true? I mean, there it is right there. That switch is true. It's nothing but a straight line. Why did it go true? Because this is telling it to go false, and this is telling it to go false. And the way the thing scans, it scans here, it scans here, it scans here, and then when it updates the output, this guy right here, the last one, is telling it to do what? Turn off. So I'm going to flip the next one. Okay? It still don't go through. Y'all see what I'm saying? Now let's switch the last one. Now all of them go through. So these up here make no difference. So the whole thing is controlled by whichever one is in the last rung. The furthest one down controls that output. The other one made no difference. So I've wasted all this time, and you understand that. So this is why we can't duplicate outputs the way the PLC scans this program. Scans this line, scans this line, scans this line. This was the last one scanned. So when it updates the output, which one does it pick up? It picks up the one that's got the biggest rung, the largest rung number. So it don't, but it didn't give me an error. So when I go back, when I go offline, and I come up here and check the program, it says the program's okay. Because everything's in the right syntax, right? You understand that? Everything's in the right syntax. So this is allowed, and this is something you got to look up. This is something you got to look out for. You can't do what? You shouldn't do what? I'm not saying you can't, because you just won't get an error. But you shouldn't use the same contact. You shouldn't use the same output multiple times. Y'all understand that? Because the other ones are just what? Just a waste. We used to do this a long time ago when PLCs are real slow. But now they're so fast that we can't get by with it. But it's not going to give you an error. So you're down here, you're hitting an input, and it looks like the rung's supposed to be true, but the output never goes true. Well, what could be the problem? You're using that same output where? Somewhere else in your program that's in a smaller line. And this happens every once in a while in this class. I've seen it happen more than once where people duplicate outputs. So we can't duplicate outputs, right? You understand that. The problem is, though, is when we check it, it don't give us a what? It don't give us an error. Because technically, it's in the right syntax. The rung's in the right syntax. So the only time this is legal is when we use these special instructions, and I'll show y'all some, these are called latch and unlatch. So notice these two have the same address. But one of them output, an output latch, the other one I'm using an output. So we check this, of course, it's going to be legal. And I'm going to come up here, I'm going to download this one. So this is the only time you should ever duplicate output. So output latch and output unlatch have to be in pairs. So every latch, somewhere you got to have a what? You got to have an unlatch. So this is just a seal-in type circuit. So I'm gonna come up here and just, I'm gonna use a momentary contact. And notice what happened. It did what? Both of them went true. And I can do this from never, once it's latched, it's latched. But if I come over and hit the what? The unlatch, and it unlatches. So this is kind of a memory circuit in itself. We can use these in pairs. They have the same address, but it's a different instruction. So this right here is a output, and that's right here. If you look up here, that's the coil that's got the L in it. So that's the latch, and right beside it is the what? Unlatch. These can have the same address. In fact, these must have the same address. They must have the same address. But you can't use the symbol to enter this one, because if you come in and type it, it's going to pop in this guy up here. So you'll have to rename this. You'll have to give this the same address, and then the symbol will pop in. So we understand. So don't duplicate outputs. The only outputs we should duplicate is the latch and unlatch. And we looked at all the rules. We looked at comments. Everybody okay? So this has happened in this class already. If it pops up yellow, it is not. If it pops up yellow, it is not a symbol. It's a what? It's a comment, right? You understand? And this happens every time too. So symbols are going to be in green. So comments are okay. In fact, they're really, really nice because this is actually this is a rung that's out of the program used to program the PLCs over on the Festo line, the 1500s. And the Germans wrote this, and they have comments on everything. So now it makes it easy for somebody like me trying to figure out why they did what they did. I can read this thing, and I don't have to figure out the program because the programmer let me know. So comments, we can give comments to rungs, we can give comments to, so I know even though it uses EM underscore stop for the symbol, he's actually put that's the emergency stop unlock circuit that would be connected. So comments are real good. If you're a really, really good programmer, you're going to use comments, but definitely you want to start using symbols because, like I said, most of your newer PLCs, they don't call them symbols anymore. They call them tags. And these tags are usually required. So that's why we're trying to get y'all used to using them here. In fact, these are actually, and notice, what do they use a lot? They use latch and unlatch. So once you learn how that thing works, they use that a lot. We're going to talk about these other instructions. What did I just do? He's going crazy. This is another output. So later on, not in this class, in fact we will, if we get into timers and counters, they're going to come in as a block instruction. So we'll get into those later on. We'll talk about the information that we would be required there. Symbols we already talked about. It says symbols with RSlogic 500. A symbol is an optional logical text address assigned to an input and output address. Right? Once a symbol has been assigned, the symbol name can be used instead of the physical address if the same device usually a contactor after this, needs to be used multiple times within the run. In European programming applications, these are referred to as tags and are required. For this reason, we're making sure y'all get used to using these things, right? We already know how to start a new PLC program. Everybody okay there? After they're wanting you to do the relay logic first, but we very seldom do that anymore. We talked about, I showed y'all how we could, how we set up the communication. This is very, very important, and I'm going to demonstrate this to you. So in motor controls, if we come over here and we have this, and let me shift this down a bit. We can pick up the bottom of the slide to make sure that's recorded. So this would be a normally closed push button. And this right here is a normally open push button. And then this right here would be contact. And this right here would be a relay coil. And we'll just call it CR for the heck of it. Now this is the way we would do this in motor control. So if I was going to program this in a PLC, normal tendency is to come up here and use this. Then I'd come over here and use this. Then I would come over here and use this. Then I would come over here and use this, right? And then I would assign this to an input. So let's assign this to input 0. We'll assign this to input 1. And we'll call this guy, we'll call this output 0. And we'll assign this to output 0. Now that's the normal tendency for us to do. We're going to have a problem with this. So if I'm going to wire this up, here's my PLC. We'll have our common. And I'd run this down here. And I would come up here and use a normally closed push button. Hook it up to input 0. Then I'd come down here and I'd have a normally open push button. And I would hook this up to input 1. And on my output side, we're not talking about we're having problems with input. Okay. So in PLCs, this is not a normally open push button. This is an examine if open instruction. And this is an examine if closed instruction. So examine if open means it's true if it's open. Of course, it means it's true if it's closed. So I come in here and I do that symbol. Right. So this right here is a normally closed contact. And I'm telling it down here, I'm telling it's true if it's open. What's the problem? Huh? This needs to be true if it's closed, right? You understand? Everybody understand that? So what we would have is we would have a problem if the electrician hooks up a normally closed contact out there, because that's what it calls for, and then they come up here and this thing starts off fault. So we'll do this, and I'll actually, so I'm going to come over here, I'm going to write this, I'm going to just do this program, so I'm going to come up here and start a new program. Okay. And then select our CPU. And this gives people that's taken motor controls, just probably gives them the most problems that they have because they learn that as a normally closed contact, but yet it's an examine if open. So I'm going to draw this program. I'm going to insert a rung. I'm going to come up here and put this guy right here. I'm going to come down here and I'm going to put this guy right here. Should have put a down drop. It's okay. Down drop, then what can we do? We can drag this into there. And then I'm going to come up here and put it here. And then I'm going to put an output into it. So this is what I see in my head. I'm going to assign this to input colon 0/0. And we'll call this stop. I'm going to assign this input colon 0/1. We'll call this start. And then I'll come up here and actually use an output. I'm going to assign this output colon 0/0. Oops. So for some reason it didn't give me an option for a symbol. So I'm going to right click on it, come down here and, oh, yeah. Can anybody see what I did? Alright, good. Let's give that another shot. I don't know what just happened. Output colon 0/0. And then we'll call this run. So okay. And then I'll come over here and assign this to that relay right there. So that's the contact being controlled by the relay. Come up, check for errors. Everything looks okay. So what I'm going to do is I'm going to come up here and close switch 0 because it's supposed to be a normally closed switch, right? You understand? Everybody understand what I'm doing? And I'm going to come down here and I'm going to download this. Looks like I've already got one out there. So I'm using a normally closed push button. And what's the problem? It starts off false. Y'all understand? So if I open this sucker up, it goes true. So that means I would be using a normally open push button for a stop button. Now what's wrong with that? So we're not supposed to use a normally open push button for a stop button. So I'm saying examine if open. This is an examine if open, and I have the switch open. So instead of using that normally stop to get this thing to work, what I had to do on my PLC, what did I do with my drawing? Weird. So this is what this is on my inputs, this is what I had to do. So I've got my plus. So instead of using a normally closed, if I use that instruction, I have to use that guy right there. And then for my start button, I'm doing this right here too. And this is input 0 and input 1. And then my program looks like this now. So what's the problem with using a normally open push button as a stop button? just so I can make my diagram look like my motor control circuit. Huh? Well, it does, because we're saying this says it's true if it's open. So this is examine if open. And is the switch open? Yes, the switch open, so it's true. So it starts off true. And then this right here is an examine if closed instruction, and that's this guy right here. So this is what I'm trying to do over on my motor control circuit. I'm trying to get this to act like this. So we're calling it stop. We're going to call this start. We're calling this CR, and I'm going to control that contact with CR. So this is a standard memory circuit. That's supposed to touch it there. So I come over here and press the start button. CR comes in. CR seals in, and now I can let go of the start button. And then if I wanted to stop, I press this one, it breaks the circuit. But in PLC program, if I'm going to use a normally closed push button, right, you understand. Over here, I'm having to use it's true if it's open. So that means if I've got this open, then this guy right here is true, and it lets the signal flow through. I press this. I think this is output 0. It closes this contact and seals in. So I'm going to come over here and go back to my PLC program. My PLC program works. It works fine now. So here I've got my switch open. I don't have it closed. I've got it open. So on this PLC. So if I wanted it to be closed, I could put it in that position right there. So that acts like a normally closed push button now. Okay. But when I come over here and look at my PLC program, it's now false. Because that is not a normally closed contact. It says it's true if the push button is open, but I have it closed. Okay. So when I come over here on my PLC and I put that switch open, now the contact goes true. So instead of me using a real normally closed push button as a stop button, I'm using a normally open push button as a stop button, which says it's true if it's open. It not only needs to be another way, a stop button has got to be normally closed. Why? Because right now I'm going to wire this guy up. If this wire breaks going from here to my control panel, and that sucker's running a 200 horsepower motor, I cannot stop it anymore. Because it says it's true if it's open, and if the wire is open, it's just like an open contact. It's just like an open switch. So what that means is, if you take motor controls, I can see it right off. And the guy that wrote this book does the same thing. He'll draw a normally closed push button in the circuit, and then he'll come over here and use an examine if open instruction. So I'm going to go offline, and I'll wire this up. I'm going to wire it up in a minute. And that's good because y'all can see how we'd actually wire these up to the PLC. Of course, I'm not going to wire it up here. I'm going to wire it up to these output panels here. So this is the only normally closed push button I have right here. And then this would be normally open. And then the other 3 or 4 are normally open. So what do I do if I'm going to wire up into it? What would I have to do? We're running syncing into it. So I come over here, my input devices are on a source, so I'm going to take my red right here, which is sourcing, and then I'll come it over here, and I'll hook it up to one of these. This is a switch, it'll make a difference. I hook it up there. Okay. So see what I've done? So now I'm bringing the plus out to my input. Then what I have to do, for every input device that I run, I would come over here and I would just start jumping this all the way through my electrical circuit. So if I wanted to hook up all these push buttons, I would, but right now all we need is two. Pretty straightforward. Syncing inputs on my PLC, so my input device has to be sourced. So and then what would I do? Well, now what I would do is I would take the other side of my push button, which would be this guy, and then I would come over here and hook this up to one of my inputs on my PLC. So we're using input 0. And then I would come over here on the other switch, and I would hook this up to output 1, and then I would bring this over to the other push button. And we'll put all these in the switch position. So now we have the circuit wired up for inputs. So what I did, I run, because my PLC runs syncing inputs, so it means my switches have the source. So I ran the what? I run the plus out, and then I did what? Then I jumped them together. And then each one of these goes to a different input. So when I press this button right here, now we got a problem with this because I'm using a normally closing push button. So what somebody would have to do, they would have to sit here all day long and hold this button, which is wrong, right? Unless I do what? Unless I come over here and use the normally open to input 0. So I'm going to go over here to the other one. I think I've already got it jumped out. And we'll move this over to here. So this is the normally open push button. So now it goes true. See that? So I'm going to start this thing up, and all of a sudden something happens, and I can stop it with this normally open push button. I can start it, I can stop it, I can start it, I can stop it. Okay, but I'm going to start it, and then this wire right here breaks. And now I'm hitting the stop button. What's the problem? I can't stop it. I can't stop it. And wires break all the time. So here I've got this 200 horsepower motor that's out there running, and I'm trying to do what? I'm hitting the stop button, it won't what? It won't stop. So what we'll do is we'll go offline. Instead of using an examine if open instruction, so I'm going to come up here and I'm going to edit. Oh, I'm sorry. Change instruction type. And notice it now this is where you're going to have to know those those 3-letter acronyms. I'm going to come back and change that to a C. And it automatically changed the symbol for me, right? So you don't have to drag it in. If you know those little three-digit acronyms, and we got a list of them, then you can literally do what? In fact, we have this guy right here. This is the entire instruction palette. I don't know if I can make it any bigger. But what I can do, if I bring this up, I can drag instructions from here. So that, if you learn those things, then that's going to be a lot faster than trying to go through all these different menus, right? Scroll through that. You can pull any instruction that supports from this guy right here. But you got to know these little acronyms, these little output enables and all that other kind of stuff. So I'm going to close this up. Where's that at? It's right there. Okay, so it's okay now. So now I'm using an examine if closed instruction. And I'm going to move this back over to my normally closed switch. and then I'm going to download it again. And it's asking me, okay, do you want to give it a revision number? Okay, yes. Go online. So now I'm using the examine if closed, and I'm simulating a normally closed switch. So I have this guy right here in the closed position all the time. So now I'm going to start it, my start button, and if this wire breaks, it still didn't drop that. What did I do? Oh, I know what it is. So here I'm going to open the switch, and what did it do? It dropped out, right? So here, now, but this looks wrong because in my relay logic diagram, it's drawn as a normally closed switch. So what people want to do is they want to use that normally closed contact center. But what you got to understand is we want this thing to be true when it's what? When it's closed, right? So on your diagram, so the next lab that you're going to do, it uses like a normally closed limit switch. Which contact are you going to use for that normally closed limit switch? You're going to use an examine if closed instruction. That makes sense. But somebody here is going to make that mistake, especially if they've had motor controls. And people that's had motor controls, this is one of the hardest things to teach, is right here. They don't really understand. They want to see it as a normally closed and a normally open contact instead of an examine if closed and an examine if open instruction. Now here, this makes no difference. This is not being controlled by an input. Where this is really, really critical is when you have this thing hooked up to an input port. And if you're using a normally closed switch, then odds are you're going to be using the examine if closed instruction, right? You understand? So this guy here is closed, but now when I come up here and start it, now it seals in, right? Like I said, this is probably one of the most often used circuits in PLCs and also in motor controls is this memory circuit. Because it gives us the ability to turn things off and on with push buttons. So instead of having switches and stuff like that, we can hit one button to cause it to start, and we can hit another button to cause it to stop. But now, if this guy right here, if it breaks, it will stop the motor. And now I got to fix it. If I use an examine if closed instruction, if it breaks or we have a failure, then I'm not going to be able to stop the thing. So on our diagrams, anytime you see a normally closed limit switch or push button, you're going to use this instruction right here, right? Everybody okay? That makes sense? We'll see, since it looks like some of y'all are not paying any attention. So program contacts that are controlled by a rungs output are simply called normally open, normally closed. Examine if open and examine if closed instructions are contacts that are controlled by physical input devices such as switches, push buttons, and sensors. And we went over there and showed you how how hard it is for RS Logic. Well, it's not once you learn it. How hard what you need to go through just by setting up the communication with the PLC. And we've had that in this class a couple of times already where you've lost that feature. So normally, one of the first things you should do, even before you start a program, is come up here, let me go offline. And do what? Just come up here to comms. And then system comms and just make sure your PLC is listed. If it's not listed or if it's got a big red X out there, it means we need to reconnect to it, right? That makes sense? And then of course using Ethernet is a little harder because you have to assign it that IP address. So luckily I've set that all up for you. So we went through that. Through DHCP, Dynamic Host, this is what automatically assigns IPs to your PLC. We're okay on syncing and sourcing. Is everybody okay on that now? And we've looked at this, we talked about this, this is the way this is not technically how, this is really the way, I have this thing wired, is, up here we have one power supply coming out of the trainer. And then, oops, I need to turn it the other way, guys. Sorry. So this is the way that our PLC is actually wired. So I have this run into here, and then I have this run into here. And then we bring this out like that. So, that makes sense? So we got one power supply. We don't have two power supplies. It's the same power supply. And I think I've got the hookup. I'll show y'all. But some of y'all are not doing that. Scan rate, the time it requires to execute the PLC ladder diagram. Scan time can be accessed in the CPU status. So over here, I'm gonna go back online. So the program's running, but right here under status, right here, what's this over here called? The It's on the test. Project tree, good. But here's processor status, and the one time we've got up here is we've got the actual scan time. Watchdog scanner, so this guy looks like it's doing it in about 20 microseconds to scan this program. Scan is how long it takes to make one pass through the program before it starts looking. That's the scan time. Every PLC that I've seen gives you the ability to look at the scan time. If you're online, you got to be online. If you're not online, it doesn't make any difference. So, scan time, math. We're not going to do math this semester. Protection. We use source. By the way, I can't do this online. Let me go offline. So when I go controller properties, this right here is actually where you give this is where you give your processor a name. So right now, every time you upload, it says untitled. But if you wanted to give the processor a name, this is where you would. So if we were connected using Ethernet, we could connect to a lot of different PLCs. Well, what we'd make sure we did was give every PLC a different name. And that way, when I'm programming, I know which PLC I'm programming. And this is where if you write, and when you save a program, the communication technique that you use is saved as part of the program. So this program was saved using that DFI, the 485 interface. But I've written a program, I did a program the other day using the Ethernet IP interface. So if I tried to run that program, it wouldn't run. It would tell me I had the wrong communication setting. So what I could do is I could take that program, and I could come in here and I could change it over to Ethernet IP and it would be okay. So that's just some stuff. So everybody okay on scan time? Does that make sense? That's the time it takes for the PLC to run through the program. What? How many times? Once, right? But it's looping. For every loop, I guess you'd say. PLC ladder diagram instructions, scans from instructions in the upper left-hand corner, reads inputs, runs logic, updates output. And that's why the last line that has that output in there is the one that's controlling it. Output energize, everybody okay on that? That's the standard one. Output latch, we showed y'all that. An output latch instruction used for latch and unlatch instructions. These have to be used in pairs, and we're not going to talk about the one shot. If you take PLC 3, we'll get into that instruction. Input scan, processor reads inputs and updates input status table. Processor executes PLC program and updates the output status table. Output status table values transfers to the output. So this is why, if you duplicate output, the last one in the rung is controlling that output. None of the other ones make any difference. We're not going to look at that. So this is a basic scan of a PLC. And it just constantly does what? It just constantly loops. Project 3, everybody okay? So program files and data files. So why they do these or not, I don't know. These status files, we have no control over those. We can't use them. We can't get into them. So I don't know why they just play them at all. But that's basically where the system and everything is going. This is the ladder. This is ladder 2, by the way. We can give it a name if we want to. So we can come up here. It's always ladder 2. But we can come up here and rename this. Call it like program 1 if we want to. Y'all see how I did that? Yes or no? Now when I do that, what you'll notice is still ladder 2. That's the data file it's taken. Now it has a name. Did y'all see how I did that? How did I do that? I come up here and did what? I right-clicked on it and chose what? Rename. So, and what we can do is I can come up here on program file, and I can do what? I can go to new, and automatically it puts it in program file 3, and then we can give it a name. So I can call this program 3. And we can give it a description, and I'm going to add this. And what you notice is now we got another program file. And what I'm going to do is I'm going to click on this, and notice now we have 2 tabs. So this program actually consists of 2 modules. It's not 2 programs, it's the same program that has 2 modules. And I can come over here now, and then I can put a program over here, right? Insert a run, guys. But all we have to do, we're not going to deal with this semester, but we'll look at this, and you need to understand that because the book does touch on this. Data files, this is what we're going to be very interested in because this PLC requires you to understand these data files. These data files right here. So data file 0, this is the output data table. So this is going to hold 1s and 0s depending on what we want to tell the PLC to do with the output. Data file 1, this is your input data table. This is where we'll have all the 1s and 0s that's going to correspond to the inputs. And of course, I'm not online anymore. But so if I come over here and turn one of these switches on, depending on the bit position, it'll come up here and go to a 1 and a 0. Now this is the one. These 2 files we don't have to specify a data file number because they're fixed. We can't move these around and we can't add multiple ones of those. Everybody okay? But over here, why we have to specify these? If I need another B file, then I can come up here on data file, and I can say new, and I can choose a binary file, and then I can give it a name, like B10, which the book talks about, and then I'm gonna say okay. Well, what now? We get another binary file, but instead of being what? Instead of being data file 3, it's data file 9. So that's why when we specify these other files, except for inputs and outputs, we have to specify a file number. Inputs and outputs, we don't have to specify 0 and 1 because those are fixed. The only way I can add more inputs is to put more modules on these things, right? So the only way I can add more outputs is to put more modules. I can make as many big binary files as I need until I run out of memory, right, in the PLC. I think this guy's got 16K in it. To us, that don't seem like much, but everything's ones and zeros. What eats up so much memory, what's required so much memory is this graphical user interface that we have. You'd be surprised how much memory it takes just to hold that image. So yeah, the first IBM PC came with 360K of memory, but everything was text, everything was ASCII. So as soon as we went to these graphical user interfaces or these GUI interfaces, then the memory in the computer had to do what? And these applications that have all these graphics in them, used to, I could put a program together and it might be 1K. Now it would be, big because now we do everything with graphics. It makes it easier on us, but it's intensive. So usually the hardest working part of the computer is the video. Especially if you're gaming, So if you're gaming and you're using a computer, then you're gonna have to have a hustle one. So input, output, status. We'll use this. We could have more status, but this is where we can go in and look at our errors. If we got any problems. Binary. We already played around with this. This is where we can use these for internal coils. These are coils that don't have to use one of our outputs, right? I already showed y'all that. And of course, we got other functions. Timers, this is where we're going to set up our timers toward the end of the semester. Right now, and we can have 256 timers. We'll look at that in a minute. 0 to 255. So we have to specify a number. Counters, we can have up to 250. In one data file, we can have up to 256 counters in one data file. But if I needed more and I've got enough memory, I could create instead of a C5, I could create a C9, right? You understand that? So that's why on those we have to specify the data file number. Control register, this is used by specialized instructions that does not use the status register. We won't be dealing with those this semester. Integers, what's an integer? What's an integer number? It's a whole number, right? This PLC only supports signed integers. Most of your newer PLCs, to give you more numbers, supports both unsigned integers and signed integers. So an unsigned integer would be without a sign. So everything's assumed to be positive. A signed integer, we can have negative and positive. Floating point, this is where we hold up with our real numbers right here. This uses scientific notation. Once you exceed the range of what we have, so it's 32 bits, we sacrifice, I can't remember, we'll look at it, but it's just like your calculator. So your calculator, as long as you're entering numbers and you don't exceed the range of your calculator, it displays them, and as soon as you do, it automatically shifts into what? Scientific notation. Well, this is true here. So this gives us huge numbers, but as soon as it shifts into scientific notation, then you lose accuracy, right? Because as soon as it shifts into scientific notation, then the number is rounded. Okay. So if we got to be extremely accurate, as long as it don't exceed the range, we're going to use integers. But if not, if we don't have to be extremely accurate, we use floating point. And this is just another B file that I created, B9. If I don't want it anymore, I can come up here, highlight it, right click, and choose what? Delete. So these other files, anything above data file 1, we can make multiple of these. So anytime we use these, we're going to have to in an instruction, we're going to have to specify the number. Now this is the biggest difference with new PLC. So with RS Logic 500, the application controls the memory of the computer. Controls the memory of the PLC. On new applications, you control the memory. So as soon as I have this binary file right there, then I'm losing. Even though I only need one bit, I lose 256 words of memory, or 512 bytes of memory. So for every bit file I create, it's going to eat up 256 bytes of memory. These guys up here eat up a lot, because this uses 3 words per timer. So that would be 3 times 256. That would be the number of words every timer data file is required. It automatically associates that memory. On UPLCs, if you use one timer, you use the memory for one timer. So that's a big, big difference that's changed with UPLCs, is we don't have these data files. These data files. By the way, the book incorrectly calls these registers. They are not registers. Registers are inside the microprocessor. These are data files. You will not see that term. If you go through all the documents for the Allen Bradley PLCs, you will not see the term register. They call them elements or call them data files. So that's the project tree. So we talked about output, scan time here, scan time, program files. So project, we call that the project tree, right? Project tree. We know this now is an examine if closed. We know this is an examine if open. Note that an examine if open instruction is not normally used for a normally closed file. Well, we already showed y'all that, right? System files, these are non-accessible to you. They eat up program file 0 and 1. You can't look at them. You can't do anything with them. So our first program file we have available is the ladder 2. Those the main ladder program. PLC projects may be more than one program file, including program files that's called subroutines. So most used programs are split into modules we call subroutines. So what I could do in this program right here, well, there it is right there, jump subroutine. So in my main program, we have a program called jump subroutine. Oops, can't put it there, Rich. And then we have the specified data file number. So what happens when this thing here scans, it hits this and it will automatically run this program right here. And then when it hits this end, it'll automatically do what? Come back to the main program. What this allows us to do, it allows us to take a huge program and split it into individual modules. And it makes the program so much, we call that structured programming. It makes the program so much easier to troubleshoot. So instead of I'm trying to find the program that controls the carousel on the Festo line. Well, instead of me going through 52 lines of code, right, to understand, I might have a subroutine that says carousel control. On the Festo, on the Fanuc robot, it has one subroutine for every little move that it makes. So when we had the Festo, originally when we put the line, we put it over here. When we moved it over there, the floor is not exactly the same, and the robot missed everything. So I had to reteach every point. Well, instead of me trying to go in and find that point, when they wrote the program, they wrote it as what? Subroutine. So I could go into the subroutine that picked up the block off the line and do what? I could teach it, reteach that point, I could reteach each point individually and keep playing around with it. So structured programs means we take a big program and we split it up into individual modules we call subroutines. And then to get to that, we use a what? JSR instruction. So every programming language I've ever dealt with has the ability to have subroutines. And you love them. After a while, you know, when I first started writing programs, I'd just write these big old long programs. And then when I'd come back later on and try to figure out, I had to figure out which line of code did what. But once I figured out subroutines, I always put the program, and then now I don't have, then I give the subroutine the name on what it does, and then it's split up out there, and I say, okay, I want to find that, I go to the subroutine, and yeah, that was a life-changing something for me, but we all learn. So all ours are going to be straight line programs. We're not going to deal with subroutines in this class. We will deal with subroutines if you take the PLC2. That's one of the things we'll look at. Like I said, the only thing we got time for in this class is to get through with the timers and counters. So we can have multiple program files. By default, we get ladder 2. And basically, if you actually look at a program, especially the robot program, the main program is nothing but jump subroutine, and all it does is just jump to all these different subroutines. It's really cool. May be in several additional main programs called or accessed by the JSR instruction, jump subroutine instruction. Selecting a main program file or a subroutine file in the project tree area. We already showed you how to do that, right? So first of all, when you create it, it don't show up. So to get it to show up, you have to come over here and just double click on it, and then the tab will be added. And once you get the tab added, then you can go between all your subroutines real easy. So how do we add them? I just come up here to program files, I right click, enter new. It's going to automatically assign it to data file 4. I give it a name, and we want to give it a name depending on what it does. I click on OK. It automatically adds it to my project tree. If I want to see it, I need to do what? I come here and just double click on it, and it pops up. By the way, they'll pop up in the arrow that you click on. So if you want them in 1, 2, 3, you need to go through them in 1, 2, 3. Because if you click 3 first, it's going to do what? It's going to pop up over there first. So subroutines, if you take PLC3, we'll deal with a lot of subroutines. If we look at the program for the Festo line subroutine, I'll show y'all some of those too. So how many program files we can have? What determines how many program files we can have? With the amount of memory we have in our PLC. So the PLC does not have infinite, but it's true binary, no graphics. So when we say 16K to us, they say, man, that ain't nuts. But there's no graphics inside that thing. It's all ones and zeros, right? So 16K we can put some pretty good sized programs in. Especially by the way, you can delete these default data files. So if you're not using timers, what can I do? I could right click, and what can I do with it? No, it won't let me delete it. It's grayed out now. Dang it. Oh, I'm not going to do it. It looks like it's grayed out. I don't know. I don't think it is. We can hide them too, but so if you never use any of these and you need the memory for something else, then you can get rid of data files that you don't want, that you don't need. But like I said, your new PLC is done away. They still have a project tree. They call it something different. But over here, you only create timers when you need timers. You only create counters, and it only eats up the memory for one timer. So they've changed that quite a bit on new programming applications. Project tree. Dedicated data files. Okay, we have inputs, outputs, status, timers. We're going to deal with C4s, C5, C6, integers. Floating point is not listed in the book. The book talks about B3 and B10, but you only get to B10 if you do what? If you create it, right? Note that some antibody PLCs allow file numbers 9 through 255 to be used, assigned by the end user to data files above 2. Controller memory, the micrologic. So this instruction memory, by the way, is in that data file. Current PLC programming applications do not use dedicated data files. So this is the problem. This is what's changed a lot on new programming applications. It's still the same, It's just that we're not really concerned with, I have 256 of these and I have all this kind of stuff. We're not concerned with that anymore. That's a good idea. Y'all just take a 10-minute break, guys. Okay, is everybody okay so far? Any questions? Because guys, I go through things pretty fast. I know this pretty well. So if you need to stop me, you need to do what? You need to stop me, right? We talked about the examiner closed, examiner open. So this is what happens is that when the PLC examines that data input table, it's using examiner closed instructions. So the one in that table is examiner open is going to say 0 in that data. So if you get 24 rows coming on that input, that's one of those instructions that input that you want to use to fix that data. But just because you see a normally closed contact in a relay logic diagram does not mean you're going to use an examiner closed instruction inside a PLC program, right? This is the syntax for an address. Everybody okay with that? We talked about this several times. So we start off with a file type, in, out, B, P, D, all different types of information. Then we put a data file number. The only time we don't put a data file number is for inputs and outputs. We can if you want to. So you can say out 0, colon, but as soon as you hit enter, the 0 is going to disappear because it knows where the outputs are at. We cannot have multiple outputs because these are physical, right? I cannot create another output file because those are established by how many physical inputs and how many physical outputs you have. Then we provide a slot number. Of course, we're using what for ours? We're using 0 because ours are internal. But if I was to slap another module on here, then I would have to use a different slot number. In the old days, it would be slot 1, but on these PLCs, you literally assign a slot number. When you configure your I/O, you assign a slot number. Then, if we're going to address a word, and our word is 16 bits, we put a dot, and then we put a word number, a word address. This is going to come into play when we get into timers and counters. We're going to have to address words within those. Okay. Well, right now, we're not addressing words. We're not addressing the whole input. So what we're doing is that's optional, right? So if we need to address individual words, we would put a word address. If we don't need to address individual words, then we can do a what? We can leave that off. Then we put a slot and we can put an optional bit address. So if I want to address a whole word, I would stop. If I wanted to address a whole word, I would stop right here. I would put this information. I'd stop right there. If I wanted to address a bit and I need and the word is default, I mean I know what it is, then what I would do is I would come over here, and this is what we're doing right now. I would come over and what? I'd leave this off, and that's what we're doing right now. Because we're not addressing an individual word, we're addressing a bit, right? You understand that? So it's understood to be word 0. Okay? Everybody okay there? So, inputs and outputs, we don't have to put that because those are physical. We can't have multiple inputs and outputs. Status, we've looked at that. We can look at hold the flags of the status. So we'll use this semester if you ever get a fault. By the way, if you get a fault, we got a PLC. Look at your PLC. The third LED from the right says what? Fault. If that ever flashes red, it's going to be you've got something really screwed up in your program, right? You understand? And the status file will show us what that fault was. Find fault indicator status bit reads the reason for the message was generated and correct the program to solve the fault. So this is where we'd go right off the bat. If I had a fault, if that red light goes on, I would go in and I examine these data files, or that data file. Timers holds information relative to the number of timers used in a ladder diagram. Depending on the size of the PLC RAM or memory, there could be timers from addresses T40 up to T4255, which means we could have 256 timers. A PLC ladder diagram can have access to 256 timers, but we got a note. Some PLCs allows us to use data files 9 through 255 for additional timers, and of course 1100 does. But the fixed PLC, the 1000, you cannot put more data files. You cannot add more data files with the 1000. We can with the 1100. So that might not be available on all of the Micrologic PLCs. The number of data files may be limited due to the lack of enough memory in the PLC. Each timer requires 3 words of memory. The book incorrectly calls these words registers. These are not registers. Registers are inside the PLC. I don't know why the guy got that term. If you ever look at the PLC PLC manual, they call these elements. So it consists of 3 elements, which would be words. So every timer you program is going to eat up 3 words of memory, or 6 bytes, right? Counters holds information relative to counters that can have any address between C5 and C255. Number may be limited due to the lack of RAM in the machine. So how many timers you can have, even though it says you have 255, if you're using all this other kind of stuff, you might not be able to get that 256 timers. Each timer requires 3 words or 3 elements of memory, so just like the timer. This thing eats up 6 bytes of memory for every timer that you use. But you've already got 256 times 3 in there already. So odds are we're not going to have to add any more timer data files, because that's a lot of timers. Everybody okay? Control registers. Control register file R6 holds 256 words. So this would be 512 bytes used as control registers. We won't use this semester because this is used by sequencer instructions and bit shift instructions. So we'll play around with that in PLC 2. Integers holds 256 words, N7 through N255, that can be used as temporary storage of integers, 16-bit size integers. Now, Jacob does.
There's one on your hat right
Jacob?
now. On your hat. There's a spider on your hat. I was supposed to take your hat.
There you go.
He was catching the nose and I'm like, what?
It was just go along for the ride, right? Okay, so I'm going to explain something to you, whether you understand it or not, that's okay. So what we've got is on our calculator, we've got a symbol that looks like this. And we call that the plus sign. But it's a symbol. So it's a symbol, and a symbol is when we use something to represent something else. So if I was looking at the USB interface and I see the plus, that is not plus, that's the non-inverted signal. And the minus is the inverted signal on USB. So this could represent anything. And then we got this other symbol like this. Now, how am I going to represent that with a binary number when I don't have plus and minus inside my PLC? We're going to have to use a bit, right? So I've come over here and I got a binary number. So let's say I got a binary number. Which would be the most, I'm just going to use 4 bits. Which would be the bit that I would most likely use to represent the sign? The least significant bit or the most significant bit? Well, where do we write this? If I come over here and I write 136, where do I write the sign at? Do I write it on the right or do I write it on the left? I write it on the left, right? So that means what I'm going to do is I'm going to sacrifice this bit right there. As soon as I sacrifice that bit, that means I lose some combinations. So what we use is if I put a 0 right there, this tells us that the binary number is plus. If I put a 1 right there, this tells us that the binary number is minus, if I'm using signed numbers. So instead of having 16 combinations, I got 7 combinations. So if I come over here and started counting, this would be 0. So we lose one of our positive combinations because 0 has no sign. I don't care what it is, right? And of course, this right here would be a positive 1. This right here would be a positive 2. This right here would be a positive 3. This right here would be a positive 4. This right here would be a positive 5. This right here would be a positive 6. This right here would be a positive 7. And now I can't go any further. Because as soon as I go one more count, it's not going to be positive anymore. It's going to be what? Negative. So how many positive combinations did I have? 1, 2, 3, 4, 5, 6, 7. We lost 0 because 0 has no sign. It's not negative and it's not positive. Okay. Now the negative number is what gets interesting. So we would think this right here is a negative. This right here is a negative 7. So a negative 1. Let me get this. Someone erase that. The erase don't pop up. So a negative 1 oh, I know what I'm doing. Hold on. So a negative 1 would be this. A negative 2 would be this. A negative 3 would be this. So to us that looks weird, right? You understand? And we can show you this on my calculator. So I'm going to come over here on my calculator. Oops. I'm going to bring up my calculator. There it is. Somehow, guys, I got mine. So I'm going to come up here on my calculator and I'm going to go to Programmer's Calculator. And then I'm going to come up here and I'm going to put a 1. And then I'm going to change the sign to a minus. And then I'm going to look at this in binary. Can you see what it is? It's all what? It's all 1. And I'm going to come up here. Of course, this is a big calculator. Let me do it in hex so y'all can see it better. It's all what? It's all else. If I come up here and go back to decimal and I do a -2, 2 minus, and now if I look at hex, it's FFFFE. Does that look weird? So this is the way your computer represents signed numbers. Now it does that because of math. So what we're trying to do is we know we have the ability to do signed math. So I'm going to come up here, and this right here is, let's say, a -5. So I'm going to come over here back to decimal, and I'm going to put a 5, and I'm going to put a minus, and then I'm going to convert that to hex. So I'll use a B for a -5. a B. So that'll be a 1, 1, 0, 1. And then I'll come over here and I'm going to look at, I know I did this, but I'm going to do it with the calculator. I'm going to put it back in decimal, and I'm going to do a -2. And then I'm going to convert it to hex, and it's an E. So I'd come over here, this would be an E. Now if I do, sorry, I shouldn't have done that. So up here, dang it. So it's -2, -2 is E. So I'm going to put +5, so +5 would be this, right? And then a -2 would be this. Now what I'm going to do is I'm going to keep my, and what is 5 minus 2? It's 3. So what I'm going to do is I'm going to add these two numbers together and I'm going to drop the carry. So this right here, is that a B? Or did I do it? I did a -3, right? Oops, sorry. Let me get this right. I lost my ring. What two numbers was I doing? Was I doing 5 minus 3? This is 5 minus 2, but I think I did 5 minus 3. Well, let me go back to my calculator to make sure. So this is decimal, so that's a -2. So that's an E, I'm sorry. Because I knew my math wasn't right. So this would be E. So 5 minus 2 should give me a 3. Well, what I'm going to do is I'm going to come over here and that would be a 1, right? Everybody okay? What I have to do here, I have to borrow. I'm going to borrow a 2, okay? 2 minus 1, that's 1. Here I'm going to have to borrow. I can't borrow from that, so I'm going to generate a borrow. This is going to be a 2, 1, it's going to be a 2. 1 minus 1 is 0, 1 minus 1 is 0, and what did I come up and get? What would this equal to? This would equal 3. So this is called 2's complement. And technically, what we're doing is we're creating signed numbers by, we used to call it, it's subtracting from zeros what we're doing. But what we're doing is we're creating signed numbers. It's called 2's complement, where I can do math without doing math, right? You understand? So notice this represents a +5. This represents a -2. But when I do the math, this is 2's complement, this is 2's complement for positive, this is 2's complement for negative, and then I can do math without having special circuits to do math, which is really, really neat. So we could come up with any number, and I can do math using 2's complement, and I do math by addition, so I subtract by addition. So the microprocessor has no addition circuits in it. It has no subtraction circuits in it. What it does, it takes the 2's complement of the bottom number, if I tell it to subtract, and adds the numbers together. Now what happens is it limits the number of positive numbers we can have and negative numbers. So here we're dealing with this guy right here. We're dealing with this slide right here. And we'll tell you why we came up with this numbers. Where you don't understand it, that is okay at this point. But when we come up here and look at this range right here, so it says I have a signed number range of plus 132,767 and a minus range of 32,768. Now this is a 16-bit number, but we're sacrificing the most significant bit for the what? For the sign bit. So if I was to bring up my calculator again, and I see how many combinations, I'm going to switch it back to a regular programming calculator. I'm using 16 bits. So that's going to be 2 raised to the 16th. That's going to give us our number of combinations. It's going to equal to that. So I have 65,536 combinations. We're only going to get half of those because we're sacrificing the most significant bit. So I'm going to come here and I'm going to divide that by 2, and that means I have 32,768 combinations. Why do we have one less positive number than we have negative number? So why do I have positive? I can have numbers up to plus 32,767 positive numbers, and I can have 32,768 negative numbers. Why do we have one more negative number than we do positive numbers? Nobody in here knows? Because 0 is the sign bit. So if 0 is a sign bit and I have all zeros, 0 has no sign. There is no such thing as a negative 0 and there's no such thing as a positive 0. So we sacrifice one of our negative one of our positive combinations is used by what? By 0. Y'all understand that? So if I come over here like I did on my slide a while ago, I started counting. So I started counting with 0. This is a positive number. Why? Because but what sign does 0 have? It's not a weighted number. So I come up here, I count 1, I count 2, I count 3, I count 4, I count 5, I count 6, I count 7. I can't have another positive combination because if I'm using the 4th bit for bit 3 as my sign bit, if I count one more, it goes negative. It'd be a negative 7. So I count my number of positive combinations. So if I say 4 bits, I say 4. I say 2 raised to the 14th. That equals 16. So that means I should have 16 positive and 16 negative combinations. 8 positive and 8 negative combinations, but I don't. I have 7 positive and 8 negative. Because we lose one of our positives because of what? 0. So this is the problem. So our PLC supports long words. So I can come over here on my PLC. Oops, my PLC, Rich. Let's see, 500, oh, it's right there. And I can come over here and I can add another program. I'm going to say new. And over here, I'm going to come over here and choose long. And then I'm going to give it a name. I can call it long 1. Or whatever it is, I can call it long 9. And then I can say OK. So now we got what we call a long data file. A long data file is not 16 bits, it's 32 bits. So if I use this data file right here, then what I can do, let me find my calculator. That's 32 bits. So I'm going to raise 2 to the 32nd. Instead of raising 2 to the 31st, I'm going to raise 32nd. I'm going to raise 2 to the 31st because we lose the most significant bit. So 2 raised to the 31st. That means I can represent signed numbers. Let's see, 2 billion, 147,487,647 positive numbers, and then 447,483,648 negative numbers, which should be enough for anything that we need to do in industry. By default, though, on the RSI, and so you don't get the L register, you don't get the L data file on the 1000, but we do get that L data file on RSLogic 5000, on the MicroLogic 1100. But we have to create that. We don't get it by default. We have to create that long data file. but I get over 2 billion, I can use over 2 billion signed numbers. And our counters are going to be limited by this. So whether you understand it or not, we lose 1 bit for what? For the signed bit. So I could come up here and I say, okay, 16 bits. If I'm dealing with signed numbers, then I would say, okay, we're dealing with words. So that'd be 2 raised to the 16th, which would give me that. Then I have to divide it by 2 because why? I lose my most significant bit, and this would give you the number of negative numbers you could represent, and we would have one less positive representation. And this is going to be important when we start talking about counters and timers because they use signed numbers too. So later on, it's going to limit our number of counts. So what's the maximum time I could put in a timer? 32,768 because it's a signed number. That's it. But I could have one timer trigger another timer. We'll talk when we get the timers and show you how we can defeat this range. What's nice with the new ones, we can specify different words. So that's the range. This is the problem we have with the integer data file, and also we'll be limited to 16 bits when we get into our counters and our timers. Floating point up to 256 per data file. These are 32-bit long because these are signed numbers. Most significant bit is 31. This is going to be your signed bit. So if it's a 0, it's a positive number. If it's a 1, it's a negative number. Bit 23 through 30, this holds the exponent, what we're going to raise the number up to. Bit 0 to 23, this is the bottom number or the base. This is what we're raising it up to. This is going to be base. So that would be like this. That would be like 5.638, right, times 10 to the 38. Well, what this would be, of course, this would be positive, so that means this bit 31 would be a 0. This right here would be this right here, and then this right here would be, this right here would be, holds the exponent, and this would be that right there. So what we can do with this is we can represent signed numbers up to 3.4028 times 10 to the 38 to a minus 3.48 times. Now we get the exact same positive though, we do negative on this because we have a bit. This has nothing to do with the way the bit is, right? But as soon as we go into scientific notation, what does that mean? It means we're going to lose accuracy, right? You understand that? It's just like your calculator. As soon as your calculator goes into scientific notation, it means what? It means the number is rounded. But a lot of times it's okay. This is when we're not concerned with the exact weight of the number. So floating points. We can have 256. Each one of these are only 2 words long, 32 bits, or 2 words long. And we can have 256 of them. If I need more on 1,000, on 1,100, I can add more. What determines the maximum amount we could do? It depends on the amount of memory we have in our computer, in our PLC. B3s. The book talks about B3s and B10s, but the only time you get to B10 is you create it. Each B data file holds 256 words of memory. So we can have B3, B255. Used by all bit instructions, used by internal relay pools. So if I don't need the output, if I don't need to turn on a light, if I don't need to energize a solenoid, if I don't need to actually generate something on the outside world, then what we will use is we'll use a internal, we call them internal coils. and we'll say B3. We have to specify that colon, maybe 0/0, right? And then we might give it a symbol. Now, what's the difference between this and an output? So, what's the difference between a B3 and an output? Somebody tell me. See, this is the program we use all ago. So what's the difference between using a B3 bit instead of coming over here and you use one of these? So how many outputs do we have on our PLC? 6. So here I'm writing a program and I've got a coil that does not need to turn on a light. It does not need to turn on a re-energize a relay. It does not need to start a motor. Its contacts are nothing but in my control circuit. Oops. If we do this, we're going to use what we call an internal coil. Every PLC supports this. This is what saves money right here. So if I do a relay logic, every relay has to have a relay. In large control circuits, 90% of the logic is just logic. It's just relays that's in there to do ands, ors, nots, nands, and ors. They don't run a motor. So if I can replace those inside a PLC program, if I can replace those with what we call an internal coil, I've just saved a lot of. So let's say I've got 100 relays out there, and 90 of them is doing control, and only 10 of them's running motors. Well, in relay logic, I would have to have 100 relays out there. But in PLCs, I don't have to have 100 relays. 90 of them I can program. It's the 10 that runs outputs that I have to have connected up to my PLC. So anytime I'm writing a program and I don't need to turn on one of these lights out here on this panel, I'm going to use one of my B bits. If I have to turn on an output, then I'm going to have to use one of my outputs. This is why we don't have to have all the outputs. This is why this guy's only got 6 outputs. This does everything that we need to do in this class. Are we going to need more output coils than that? Yes, but most of them is going to be what? Bit files, right? You understand? This is very, very important concept to understand. This is what makes PLCs. This is why we're using so many PLCs, because it saves so much hardware. It saves all these control relays. There's no such thing as a control relay in a PLC. So a control relay is a relay whose contacts are in the control circuit. They're not in the power circuit. So this is actually a PLC program I'm fixing to bring up for you. Yeah. So these are latch unlatch. Can you see what they're using in? They're not using out. Why? Because it don't need an output. It's strictly in there for what? It's strictly in there for the seed. You already know all this. You can come up here and take the class for me. So look, all these are what type of files? These are all B3, B3, B3. Look at, if they had to use an output for every one of these, so there's 6, right? There's 6 already. There's 8, so now I'm screwed, because I've only got, I don't have this many outputs. But this guy here does not control anything. It doesn't turn on a motor. It doesn't turn on a light. All its contacts are within the program. So we call these internal coils. Alan Bradley calls them B's. Siemens calls them M's. For memory coils, they call them memory coils, which makes more sense. But every PLC programming language I've ever programmed gives you the ability, and this is the power of the PLC. Not only can we change it, we can do what? I mean, we don't sacrifice one of our outputs. So these V3s, and we use them for different things, but that's one of the main things we use them for, is to do what? Is to use these for internal coils. So right now we got 255 of them, 16 bits. So that means right now, just using B3, I got 16 times 256. So that's a lot of internal relay coils we can have, right? And of course we use them for other instructions too. That if you take PLC 2, you'll see what else we can use these memory coils for. Latch and unlatch, everybody okay on that? Showed y'all that already. That's the only time we should duplicate output addresses for latch and unlatch. And you saw that program used a lot. PLC modes, we already know these. So we have 3 modes we can put our PLC in. Program mode, this is when we can download a program into it. Run mode, this is when the PLC runs the program, whether you have a computer attached to it or not. This is the mode we're using. We're using remote mode, which allows us to do what? It allows us to change between these modes without using a switch or sometimes it has a switch on it. Sometimes it don't. Ours don't have one. So let me. So to get to ours, I would go to escape. Mode switch. And this is where we can select the mode. So right now we have it set up for remote. If I had it set up for program, I could not download a program into it, right? I'm sorry. It wouldn't run the program. If I had it in run mode, I couldn't download a program into it. So if we have it in remote mode, what does that allow us to do? It allows the application to switch it between those 3 modes. So that's why we get to it, if you wanted to do that. Somebody in this class had that. They tried to download the program and it wouldn't let them because it was in the what? It was in the run mode. It wasn't in the remote mode, so the application could not switch it for them. It's kind of misleading because it says, do you want to go online? But you're already online when you downloaded it, right? You understand? So most PLC calls that monitor. If you want to go to monitor mode, which allows you to monitor the condition of your logic. So downloading and troubleshooting, we're okay on downloading. Everybody's done that several times already in this program. PLC will be placed in the run mode. By the way, when the PLC's in the run mode and you disconnect, even though you got it in remote, if you disconnect the cable, it's going to be in the run mode. Your computer does not have to be connected to the PLC when the program is running, right? You understand? Now, that would be awful if you went down to browser and every PLC had a computer hooked up to it. So once the PLC's in the run mode, it's going to do what? It's going to run that program until you take it out of the run mode. So this is a program. So let's see if we can enter this into the PLC. So we got a normally closed here. So I'm going to come over here and bring up my program. Went right past it. Okay. I'm going to come up here and do a new program. I'm not going to save this because that's just garbage. We're gonna come up here and select our PLC. So this should be standalone. This right here should technically connect to L2, but I can't connect it to L2. So what can I do? You see what I'm saying? Yes or no? Well, we only have one output down here. We have two outputs here. So this is what we would have to do on this one. So I'm going to get rid of this one. This right here is going to be okay. I'm going to put that right there. And then what I'm going to do is I'm going to start another run. And then I'm going to come over here and I'm going to put an examine if open. And I'm going to assign this to the same switch. So technically that's the same thing, right? You understand? And then now what I can do is I can come over here and put a down drop down here. And put this, and then I'll bring in a relay. And then I'll put a down drop right here. Drag this into here. And then we'll use another one right here. Okay. Now down here, these two things are controlled by the same stop. And then down here, this is going to be another start, right? Input colon 0/1. Oh, I assigned that to one. So, input colon. And that's another nice thing about using symbol, because if it pops up there, it lets you know you've already used it, right? See? No, it won't let me do it now. So input colon 0/3. We'll call this start 2. And then this right here is filled in by the run. This right here is filled in by the run. But this over here, these have got, since these turn on motors and turn on relays, then we got to use what? We got to use outputs, right? Now this actually shows the motors, so we would be connecting these to our outputs. So I'm going to check for errors, and everything looks okay. So sometimes, so this is the same circuit, but what I've done, we can duplicate inputs. So even though I got one push button, now in motor controls, we would have to use multiple contacts. But here we can use the same contact how many times? We can use it as many times as we need, right? You understand? So even though I physically only got one contact hooked up here, so now we can do what? So right now we're offline. So what can we do in offline? We can program. We can edit our program, right? Then we can go up here and we can download, so it goes online automatically. Give it a name. What's this figure in the book? Anybody got their book open? I don't know. Let me call it number 5 right now. Well, then it says it's going to do what? It says, okay, you're going to download this, and why is it giving you this? Because the program that I got in there now is going to be what? It's going to be replaced, right? So technically, how many programs can we have running inside the PLC at one time? Now we can have multiple subroutines, but one program. Then it's going to switch to the run mode, and then it's going to ask us, do we want to go online? Now this one, when we go online, it automatically goes to the monitor. So right now, my normally closed switch, push button, even though we're using what appears to be a normally open contact, that is an examinative close. So since I'm using a normally closed push button, I'm using an examinative close instruction. Press the run. It seals both of them in, right? Hit the stop, stops both of them, or I can come down here, and I don't have switch 3 hooked up, and I can jog this one. So if I use this one, it seals both of them in. If I use this one, then this is anybody know what jogging is? What's jogging? This is when we run motors in burst. We don't want them to run, we just want to move it so far. We use this for positioning. So when we go over there and we move the robot, we call that jogging. So if you're taking the robotics courses, you get that teach printed and you're manually moving the robot with those pins, those buttons on there, you're jogging the robot. So here I can seal it in. Now both of them run. I hit stop, and I can use switch 3, which I don't have it hooked up to a manual. So this is this program. So sometimes you've got to think, I didn't have any problem with the L1 side. Where I had problems is that down drop had to go all the way to had to go all the way to L2, and I couldn't do that, right? Does that make sense? Well, I guess I could. I could have figured it out. I think I could have pulled this one into it, but that's okay. And what's nice about this is inputs, you can use as many, even though you only got one push button, technically you can use them as many times as you want to. Output addresses, we should only use what? Once, unless it's unless it's a latch or unlatch instruction. Everybody okay? So, by the way, in your book, they're going to call this CR1 and CR2. That's non-existent. They both get the same name because they're controlled by the same relay. So in your lab book, you need to just mark off that right there and just call it CR. So what we do is we just give the contacts controlled by these output devices, we give them the same name. But in the textbook, anytime you see CR, then you're going to use a what? You're going to use one of your B3 files. So that means a control relay. Control relays are relays whose contacts never go outside, right? You understand that? And we'll have a lab on that too. Of course, we know how to wire these things. Ours is a little different. So ours is technically actually wired like this, guys. So this wire is non-existent. This wire is non-existent. So I have a no, that's not. I can't do it like that. So I have to draw it the other way. When we look at I/O, I'll show you how the PLC is actually wired. So this is the way we have two commons, right? And we're running syncing inputs. So our input devices have to be sourcing. And then we're running sourcing outputs. So our output devices have to be syncing. So this is what you're supposed to be doing to modify your circuit, right? And then over here I have a normally closed push button. Hooked up to that guy. Here I have a normally open push button hooked up to that guy. And I don't have anything hooked up. But over here, this is where I would put the motor relay. And then right here, it depends on the bell. This is where I'd actually put the bell. So very seldom does a PLC actually run a motor. Most of the time we use the output to bring in a motor relay, and then the motor relay runs the motor. Now this little motor that I've got on these, the PLC will run these because these are little tiny motors. Well, it's kind of different, and I'll show you how it's actually wired up when we get to our PLC. The problem is that if I do it like that, I don't establish what the common is right here. So this is the way it actually works. Is I come up here and the power source would actually be connected like this. Let me get back to this where I have these syncing and sourcing things. But that's a really good point. But to actually see it, we'd have to understand this guy right here. So this is the way we do it. So what we do is we have a common that we don't see. This is inside the PLC. So this is actually the input port itself. So sure, I could use one power supply, but what I would have to do is the battery. This one would be connected like this, right? For us. And then I could take this. Then you're right. I would take this same one right here, and this would run right there, and then this right here would run. Oh, sorry. So we're running sourcing outputs. So that's right. This would run right there, and then I'd run this over to here. But still, it's one battery source. It's just the way the book is laid out. We have to draw it as two, and it don't show us this common right here that's actually on the PLC itself, right? That makes sense. So you're right. We have one battery. I have one power supply. And we're power, even though the trainer, it gives you this in the technical manual. The actual PLC has a power supply built into it. If you look at the two right-hand side, you'll see it's got plus and minus. But it's not it doesn't supply a lot of power. So if you run push button, it will not run outputs. It tells you that in the book. Not in the book, in the technical manual. It can run some inputs and it can run some solid state sensors, but it can't. So normally what you'll find is the PLC will have an external power supply. In fact, on both the lines, we looked at those the other day, right? Both of those have external power supply. And that way you specify what power supply you need as long as you don't exceed the rating of these guys right here. So these guys are going to be rated to provide a certain amount of current. You can't run a load, but it's usually around 2 amps. Well, the problem is that little old power supply there cannot supply 2 amps. So if you did use it to run inputs, all you had was push buttons and stuff, then that would be fine. But normally the output power supply is going to have an external power supply. So 2 amps, I know we can't run a 10 horsepower motor, but with 2 amps, we could definitely pull in a motor starter, and that motor starter could run that. So this is technically the way it's wired. And then this right here would actually be the actual input that's connected there. Some PLCs, this is fixed, and you're not able to configure it for syncing and sourcing. Ours is. So, but it's not all. We can't configure all the inputs. So the first 6, 0 through the first 4, 0 through 3 has its own common, and then 5 through 9 has its own common. So we can set 0 through 3 syncing and 0 through 4 sourcing. Of course, what we've done is we've set ours up. No, I still have this backwards. Yeah, I got this backwards there. Nobody caught me on that. So what are we running on our PLC? We're running syncing inputs and sourcing outputs. So I'd have to draw that a little different. So this one, the negative would have to be connected here, and the positive would be connected there. And then what I would do is this right here would have to go right there. And then this right here would have to go over here on our single power supply. So I had ours connected backwards. So this is the way our PLC is actually wired. But I had to jump them. So if you actually look, if you can actually see the plus going up to the. You can't see the minus because it don't have a color code on it. But you can actually see this wire right here that's got the red stripe on it. So that's plus 24 volts. And then what I've done on yours, I've got all the commons. So that's common, that's common, that's common, that's common. I got them all just jumped together. So that means I'm running sourcing outputs. So if I was going to hook up an output, I would run the minus over to my output device. That makes sense? Yeah, good point. But the book's not laid up there because they have the common up there, so we just draw two power supplies for this. Just get your understanding for thinking enforcement. So that's a good point. So yeah, we usually only have one power supply, and it's up to us to either wire it right. So like I said, some PLCs you don't choose, but this PLC gives you the ability to do that. And Allen Bradley's good at that too. A good question. Where are we at? Data files, project tree, system files, which we don't have. So our first program file actually falls on ladder 2. The other is actually internal programs. And why they put those up there, I don't know, guys. We can't even get into them. It talks about assigned number ranges, and this will become important when we get into counters and timers. We talked about the modes, looked at this program, looked at this guy, he drew them. We talked about latch and unlatch, right? Everybody okay on those? And we'll have a lab on those. By the way, this is called the user. I'll get it in a minute. So this up here at the top, we can add and subtract stuff from this menu right here. This is actually where your bit files are at. So this is where your examine if close, examine if open, output enable, output latch, output unlatch. Then we have one shot rising, one shot falling, which we won't get into that in this class. But one shot means it only goes true during one scan, and we use that for a lot of things. The Festo uses it to configure all the output from start. But what we have the ability to do is we can add things to this. I'll have to go back. I know how to do it. It's been a long time since I used these, but I'll show you how you can add and take away. So mine has under my user. It's got, y'all don't have all these. Count down, count up, label, JSR, jump, CTU, because these are the stuff we use in PLC2. In fact, I need to take those away because we don't use RS Logic 500 in PLC2 anymore. We use Studio 5000. So I don't need those up there anymore because we don't use them in this class. But we can add to or subtract from that. So what you do is any instruction that you're going to use all the time, instead of trying to go through all these different menus down here to find the instruction, if you've got an instruction that you use all the time, you can put it in this user menu up there. And even Siemens has it. Siemens is a little easier. The actual project tree is on the right-hand side, and you just grab an instruction and you drag it up there. And if you don't want it, you drag it out. So it's a lot easier on here. Here we have to bring up a menu, and I'd have to go back and find it, and we select what we want to add and what we want to take away on that user. I'll have to read that up and find that. These are all that. So the only thing we're going to get to here is we'll use timers and counters. We're not going to use bits because all the bit instructions that we're going to be using is already in the user. That's by default. And we're going to use timer counters. Here's input output, but we don't need to get there because why? I'm sorry. These are instructions that we're not going to talk about. So basically, they've already got these three. They've already got this, which is always in the user. The create a new rung and the down drop. Then they give you the output, the examine if close, examine if open. They give you the output enable, the output latch and output unlatch. These when you install RS Logic 500, you get those automatically. But like I said, other programming languages has that also where you could put most often used instructions instead of you trying to go through all the menus. Okay, last thing we're going to talk about is the force and the force. May the force be with you, right? So when I come up here, I'm going to bring up Ars Logic. Not the programmer, it's this guy. And you notice right here in yellow, we have what we call force. Okay. So what we can do is we can force outputs and we can force inputs, which means I can cause this switch right here to get this input to go true, even though the input device itself is not true. So we have this guy right here called force. I'm going to bring up force inputs. And right now they have dots in there. And I'm not going to hook up anything. I'm not going to push a button over here or anything. What I'm going to go over here on input or 1, which is this guy, input 1, which is this guy right here. I'm going to come over and click on that, and I'm going to put a 1, and I'm going to hit enter. And that guy went what? It went true. And it gives us this big red thing saying it's being forced. Now this is a great troubleshooting aid. It allows you to basically check a program out even if you don't even have any real inputs hooked up to it yet. So you can say, okay, this is my sensor for my air pressure. I don't have it hooked up yet. Well, I can check the controls to see if it works. I can come over here and click on it again. And I can hit a 0, and then I can hit enter, and it turns it what? Off. This is called forcing. Now, the problem with forcing is that if there's any safety built into this thing, you just overrode it. So when you start forcing contacts, you better know the consequences of forcing the contact. Somebody that's in my other class know this. We had a guy at US Steel that got killed because somebody forced the contact. He forced the wrong one. So he was working in the top of number 8 blast furnace. That's when they used to make iron out there, which they don't make. And that was a positive pressure furnace. So all the material was fed up to the top in a conveyor belt. And they would open a hopper door, drop it down, and then open another hopper door and drop it in. And they was having problems with one of the hopper doors. So they locked it out. They did everything they needed to do. And he wanted him to go down there and force the contact, and the guy went down there and forced the contact on the other hopper door, which they didn't do one. And it came up and it cut him in two. From what I heard, I went over there, thank goodness. They brought him down in 2 pieces, killed him instantly. So when you force a contact, you better know sure what that's going to happen, because right now I just turned that motor on. So this motor right here just did what? The bell's ringing, I turned that motor on, and that push button wasn't pressed. Now how I get rid of this? So right now I can't do anything but put zeros, and I can put 1s in there. So what you have to do to get rid of it is you have to come up here and highlight it, and then hit your delete key, and then hit enter, and then it'll go back to a dot. So what I just did is I just turned force off. So we can force any input. All we need to know is the address. So there's address. So that guy right there is closed now. I can come over here and I can get 1. I can highlight that and I can make it go to a 0. So even though I've got an input over there that's controlling that, I can override that input. So like I said, you need to be safe with this, but you need to understand it, because this is a valuable troubleshooting tool. So I've got a sensor out there that's not doing what it wants to do. And it's not something that's really needed, but it's stopping the line. Well, I can override that sensor, right, to get the thing back into production, and maybe some human can replace that sensor. So that happens a lot. So how do you get rid of it? You highlight it again, and then do what? Hit delete on your keyboard, and then hit enter, and that'll turn the force off. I'm going to bring up the output. So right now this output is what? It's off. Here's output 0 right there. I'm going to come up here and enter 1. I hit enter, and what did it do? It turned on, right? But it tells me it's what? It tells me it's what? It tells me it's forced. So what we need to do, and I can force the B3, but I just turned that output on. Is this rung true? No, the rung is still false. But we can force outputs or we can force inputs. All we have to do is bring up the data table. Y'all see where that's at? Not the data table, the force table. So we hit delete. So we come down here, right here, and right here where it says force files, this is where I bring up the actual force so I can force what? I can force inputs or I can force outputs. These are data files. This actually shows you the state of these switches. So there's input. So if I come over here and press these, you can see these are actually responding to it. So these are the actual input data files that shows me the condition of all these switches. So this is what your so the PLC program is not actually reading the input. Your PLC program is reading the data file. And then the hardware inside the PLC is updating the data file. So when you store a 1 in an output, you're not actually storing the 1 in the output, you're storing it in the output data file. And then the hardware reads the output data files, and every time it sees a 1, it turns that output on. So that's a perfect example of the use of a B3. So in this book, if you ever see a CR, you're going to use a what? You're going to use a B3, right? You understand? In real life, it might not be CR. It might have a name, but if you've got a relay coil that does not need to control an output, you're going to use a memory. And then I showed y'all that on that Festo diagram. How many memory coils did they use? I mean, they were up to 10. It was up to 9 already. But they didn't have, all those was in there was for decisions to make sure this happened before that and that happened before that before something happens, right? You understand? A sequencing, setting up a sequence. So everybody's okay on force. Every PLC I've ever seen does it. Some of them are more critical. Siemens, you got to go through a technique to set it up. You have to establish a force file. So if you force on a Siemens PLC, it takes some work. This guy right here, you just bring up the force data file and you force it. So this guy is really easy to kill people. So be real careful on that. So this shows you that on PowerPoints. This is actually a force conditions method for testing the PLC system without actually closing or opening an input valve. So literally I could write a program and not even have the inputs hooked up to it, and I could do what? I could force this sensor, I could force that to see if it's going to work. So we already showed y'all this. Everybody okay on turning it off and turning it on? So once you select the bit and you put a 1 in there, then it's turned on. If you put a 1 on it, then it's going to go true. If you put a 0, it's going to go false. How do we turn it off? Well, we highlight it and hit what on our keyboard? We hit the delete key, right? Everybody okay there? That's the way you turn it off. So technically on this thing, it's even though the force is a powerful tool for troubleshooting, using the force instruction in an industrial plant has the potential of causing what? Fatal injury. So when you force a contact out there in the real world, in the Navy, when we was going through our A school and C schools in the Navy, they say, when you get into the fleet, this is the way we do it in school, but when you get into the fleet, you gotta be with this. Run mode, and the PLC is the run mode, online monitor. So we can be in the run mode without having the PLC hooked up. Everybody understand that? So once you switch that server to the run mode, it's going to do what? It's going to run the program, whether the computer's hooked up to it or not. It's just that if we switch to the online mode, we can monitor our contacts, which is a great troubleshooting tool, guys. I mean, it is unbelievable how much that's helped us. We're not going to print. Y'all don't have the ability to print anyway. But if you come up here and look at this option, so I printed off every one of these programs for the Festo line. But if you got a printer hooked up, you have the option to do what? You can print the report, you can set up the printer, you can print the program, actually print the program off, which is a lot better. It's like me, when I read books, I like to have hard copies in my hand. A lot of people like to do online. When you see a program like this, it's better to me, I like to have the program out on paper, because then you can do what? You can make notes and scratch stuff out and all that kind of stuff. So you can print, every one of them gives you the ability to print the program out on a printer. But you gotta watch out, because some of these programs are really, really long. You might have to have a lot of paper. And I think that's it, guys. Print, preview, print, reports. We can run reports. And we're not going to do that. So processor information report, channel configuration. And of course, we're not going to do any of this semester. So this is all in the textbook. So any questions on what we went over? So how far can we get in our labs? When we come in. So Monday is test day, so I'll make the review available as soon as we get out of class. So we have a test coming up Monday. And then let me bring up our lab